This is part 2 of the review. Let's do number 11. The windshield wipers on a car have not been working properly. The probability the car needs a new motor is 0.55. The probability that it needs a new switch is 0.4. And the probability that it needs both is 0.15. Well, remember, both means intersection, M and S at the same time. What is the probability that the car needs neither a new motor nor a new switch? Well, neither one is just the opposite of one or the other. And I think in this case, it's probably easier to find the probability of motor or switch, one or the other first. And then we'll just subtract that probability from 1 to get the probability that it needs neither one. So let's use our rule again. That's the probability of the first one plus the probability of the second one minus the probability of the intersection. And we're given all of those. M is 0.55. S is 0.4. And the intersection is 0.15. So I get 0.8. But remember, we're actually looking for the probability that they need neither one instead of one or the other. So that would just be 0.2. 0.2 is your actual answer. A sushi restaurant has prepared 34 portions of seafood, one of which has been left out too long and spoiled. 18 of the 34 portions are served randomly to customers, but we just have one that is spoiled out of the 34 portions. What is the probability that at least one customer will receive spoiled food? So we're looking for the probability at least one spoiled is served. And once again, you see that phrase, at least one. It's probably easier to find the probability of the complement, which is no spoiled portions are served. So let's see if we can figure that out. Well, first of all, let's figure out the number of ways for us to not serve any spoiled plates. And that's really the same thing as saying they're all good that we served. So how many good ones did we have? We had 34 total, and one of them was spoiled. So that means we had 33 good plates, and we served 18 of them. So it looks like 33 choose 18 is the numerator. That's the number of ways that all 18 could be good, because we can only choose them from the 33 plates that are good. But what is the total number of selections? Well, there are 34 plates, and we're serving 18 of them to customers. So these numbers are kind of huge. And this one says 3 places. I get 0.529. Let's move on to number 13. We are drawing a single card from a standard 52 card deck. Find the following probability. The probability that it is club, given that it is black. You know, the quick way to do it is, it's a black card and half of them are clubs. So the answer is just 1/2. But you could also use the formula too. It's the probability that it's a club and black divided by the probability that it's black. And I'll show you get the same thing either way. Well, what's the probability that it's a club and black at the same time? 13 out of 52, because there are 13 clubs in the deck. And 26 out of 52 of them are black, so the 52s cancel, and 13 over 26 is 1/2. So whichever way you want to do it. Assume that 2 cards are drawn from a standard 52 card deck. Find the following probabilities. First, in part A, assume that the cards are drawn without replacement. So we'll make a note of that. Find the probability of drawing 2 face cards. And remember, the face cards are Jack, Queen, King. We don't assume 10 is, just Jack, Queen, King. So on this one, you're supposed to multiply 2 different ratios together. So let's start with the probability the first one is a face card. Well, how many face cards are there? There are 3 ranks, and for each rank there are 4 suits. So it sounds like there are 3 times 4, which is 12 face cards total in the deck out of 52. So that's the probability the first one is a face card. But this one is without replacement. So we're throwing the first card in the trash. That means there are 51 left to choose from, and there are just 11 face cards left to choose from. So 11 out of 221. And part B is actually easier. This one is with replacement. That means we put the first card back in the deck. Well, the first factor is the same. But in this case, the second factor will also be 12 out of 52 because you're putting it right back in the deck. So let's try number 15. Okay, so this is the one where you have to consider 2 different orders, but once again, we're picking 2 cards from the deck. And once again, part A is without replacement. Well, the 2 cards this time have to be a club and a spade, but in either order. So let's assume that the club is first in the first case. Well, how many clubs do we have? 13 out of 52 of the cards are clubs. All right, but this is without replacement, so we're throwing that card in the trash. We have 51 left to choose from, but we still have all 13 spades left to choose from. So that's what we get for case 1. Now let's assume the spade is first. And I know 13 out of 52 of them are spades. But we're throwing that card in the trash once it's been chosen, but we still have 13 clubs left to choose from. So just add these 2 numbers together. And I get 13 divided by 102. All right, now part B is the one that's with replacement. So that should actually be easier. So you could assume that the club is first. And I know 13 out of 52 are clubs, but we're putting it right back in the deck. And I know that 13 out of 52 are spades. And if we assume the spade is first, you're going to get the same thing. 13 out of 52 are spades, put it right back in the deck. There are still 52, but I've got all 13 clubs left. So I end up with 1/8 when I add those two numbers together. And this should be approximately 1/8. Let's move on to the next one, which is number 16. A person draws 3 cards without replacement from a standard 52 card deck. Find the probability of drawing exactly 2 diamonds. Okay. So this one is a little bit tricky, and I don't think in this case, because we have 3 cards, we want to consider all the different orders. I'll show you a better way to do this problem. But we're looking for the probability we get exactly 2 diamonds. All right, well, let me show you how to do it. So first of all, let's decide what the sample space is. Well, we're choosing 3 out of 52 cards in this particular experiment. So that's the number of ways that that can happen. So what you usually do on this kind of problem is figure out the number of ways to choose the diamonds first, and then figure out the number of ways to choose the non-diamonds second. Well, I know that I have 13 diamonds total, and I want 2 of them to be chosen. So that's the number of ways that we could choose the 2 diamonds, because we're supposed to have exactly 2 diamonds. Well, how many non-diamonds are there? 39, but I just want to choose one of those guys. And so if we multiply those 2 numbers together, that should be the total number of ways to get exactly 2 diamonds and 1 non-diamond. So that's going to be a little tricky plugging it into the calculator. And on this one, they want a fraction and not a decimal approximation. Let's move on to number 17. So once again, I have a table I probably need to fill in for you. And I think it would be good to do that. And that good, poor refers to the service. All right. Find the probability the service was good given that the meal was dinner. So it is given that the meal is dinner. That means we only focus on this row. Remember, whatever the given is on these kind of problems, you only focus on that row or column. So given that the meal was dinner, what is the probability the service was good? Well, out of all the dinner people, 46 out of 77 said the service was good. So that's the answer. So almost better probably to not use a probability formula in that case. And they do want a fraction here. And it doesn't reduce. 46 divided by 77. And I think I'm going to skip number 18. It's very similar to the one I just did. And I think this video is long enough as it is, and I don't want to do another chart. But just focus on the row or column that is the given. in number 18 as well. Let's try number 19. A certain game consists of rolling a single fair die. If a 4 or 5 comes up, you win $8, otherwise you lose 4. What is the expected value? So this is from the last section. So if a 4 or 5 comes up, we win 8. But only 2 out of 6 of the numbers are 4s or 5s. And all the rest of them are losers. And we lose $4 if we don't get a 4 or a 5. So notice that ends up being 0. So this one is definitely a fair game. $700 chances are sold at $4 a piece for a raffle. There's a grand prize of $700, 2 second prizes at $275, and 5 third prizes of $100. Calculate the expected value. So we have 700 tickets total. $4 a piece. So we've got 1 grand prize for $700. 2 second prizes at $275. 5 third prizes of $100. So what is the expected winnings in the long run? Well, we've got 700 tickets. There's only 1 grand prize, so the probability of winning of that is 1 out of 700. But if you win, you get $700. But make sure you subtract the price of the ticket. Now we have 2 second place prizes. And in that case, it's $275. But again, you have to subtract the price of the ticket. And then we have 5 third place prizes of $100. But don't forget, most of the time you're going to lose. It looks like there are 8 winners total. That means there are 692 losers. And for them, they just lose their $4. So let's plug all that into a calculator. And I get negative $150. So on average, you're going to lose about $1.50 every time you play. Okay, so if the game is not fair, and it is certainly not fair because the expected value is not 0, determine a price for playing a game that would make it fair. So remember, here's the formula, and we did this on the last video too, I mean the expected value one. It's just the expected value plus the original price of the ticket. So to make this thing fair, we would only charge $2.50 per ticket. And the idea is, when you pay $4, you lose $1.50 every time in the long run, every time you play. So how do you make up for the $1.50 that you lose? Just take it out of the price of the ticket. One more, number 21. A card is drawn from a standard 52 card deck. Calculate the expected value for the game. A player must pay $7 to play, which must be subtracted from the winnings. If a spade is drawn, the player wins 16. Otherwise, they lose their 7. Okay. So they only win if they get a spade. And the probability of that is 13 out of 52. But if they win, they get $16. But remember, they had to pay $7 to play. But that means there are 39 losers. And in that case, they don't get anything. They just lose their $7. So let me plug all that into a calculator. So I get -3. So don't play this game. You're going to lose $3 on average. So what would be a fair price? Well, just take the expected value and add it to the original ticket price, and that gives us $4. So that should do it for this video.